Well, on the one hand, from the side, you can see this is about trigonometric identities, and these are new identities, not our basic identities. But we use our basic identities over and over and over, and we need to become very familiar with them. Now, to accomplish dealing with new trigonometric identities, we need to practice a lot and be very good at manipulating trigonometric expressions. And when I say manipulate, being able to multiply trigonometric expressions, being able to factor trigonometric expressions, being able to add fractions involving trigonometric expressions, all the things we do in algebra, except now we're doing them based on trigonometric expressions instead of x's and y's. And so you can see here our very first example is about simplifying a trigonometric expression by the process of factoring. This is what I've noted here. So here is the way I've started this. I took the expression, of course, wrote it here, and then put equal. Now here's what I noticed, because I'm told I'm going to really factor this kind of ahead of time. And I notice that this left side is of form ab squared minus a. That is, here's a, b squared minus a. In other words, sine of theta is a common factor. That's really the critical issue here. Sine of theta is a common factor. So I factored out sine of theta, and that left in parentheses cosine squared theta minus 1. Now here comes the tough part of this. Whoops. I recognize cosine squared theta minus 1 not as a specific, but as somehow related to an identity that involves sine squared theta and cosine squared theta. See, there's this identity that involves sine squared theta, cosine squared theta, and a 1, the major Pythagorean identity. And so this involves cosine squared theta and a 1, and so it makes me think of this identity. Now, if I look at this identity and I subtract cosine squared theta on both sides, I end up with sine squared theta is equal to 1 minus cosine squared theta, which is not what I have here. In fact, this is exactly the opposite of that. And I notice that if I were to factor out a negative 1 from here, I could get something that looked like this next line. See, here's my negative 1. Negative 1 times 1 is minus 1. Negative 1 times negative cosine squared theta is positive cosine squared theta. So the significance of this is now in these parentheses, I have something that I can replace and make it simpler. I can replace this with just sine squared theta. And so that's what I've done on the next step. I replaced 1 minus cosine squared theta with just a sine squared theta. And that was a critical step to recognize what I needed to do between step 1 and step 2 here. That's very important. Now, of course, it's like a negative x times an x squared. That's a negative x cubed, isn't it? And so that's what I've written here. Not, of course, x cubed, a negative sine cubed theta. And so we have simplified that expression from a couple of terms to one single term. Now, there's actually a little more straightforward method of doing this, and I really wanted to point out the way I thought about this ahead of time to change it into a way that was useful to me. But here's an alternative method. So let me write in here that I could have taken my original expression, here it is, and I could have thought, oh, cosine squared theta. Now, cosine squared theta is related to sine squared theta plus cosine squared theta is equal to 1. And if I wanted cosine squared theta, what I could do is subtract sine squared theta on both sides. So that would give me cosine squared theta up here is equal to 1 subtract sine squared theta. And that's what I've done. I replaced cosine squared theta with 1 subtract sine squared theta right here. So now it reads the original sine theta times, instead of cosine squared theta, 1 minus sine squared theta, and then minus the sine theta. Now, what I've done next is I've actually multiplied out the sine theta I've distributed it with what's in the parentheses. So sine theta times 1 is certainly just sine theta. Sine theta times a negative sine squared theta, of course, is negative sine cubed theta. And then I still have this subtract sine theta at the end. But now if I look at this line, I have a sine theta and subtract a sine theta, which is just 0. So that leaves only negative sine cubed theta at the end, which of course is exactly what we had up above. And this is a little more straightforward, and probably what I would really have done if I was trying to simplify this. I would have experimented and see if that would have made it simpler. Now let's look at another problem on the next page. Okay, we're going to continue with the idea of factoring, and I've actually got 3 different things I want to factor here, so just to remind you of techniques, really. So the very first example you see, we're supposed to factor secant squared theta minus 1. Now, hopefully from algebra, you are familiar with the way to factor the difference of 2 squares. And so what I would hope you could think here is comparing secant squared theta minus 1 to an a squared minus 1. Now in the case of a squared minus 1, we recognize that as the difference of 2 squares, and so that would factor as an a plus 1 times an a minus 1. And so we use that same concept here, where instead of an a, we have a secant of theta. And so we could factor the above Well, I'm having trouble. Let me pause just a second. Okay, I think it's fixed now. The above, we could factor secant squared theta minus 1 as a secant of theta plus 1 times a secant of theta minus 1. And it's just that thought process that's very important to us here. On this next example, you see we're to factor 4 tangent squared theta plus tangent theta minus 3. And we refer to this as of the form of quadratic form is what we call it. See, and hopefully we can begin starting to observe, notice these things. See, if I had, instead of a tangent of theta, what we would see above would be 4 times, instead of tangent squared theta, it would be u squared if I let u be tangent of theta, plus a u instead of tangent of theta, and minus a 3. And so that looks like what we would have as a quadratic trinomial that we have lots of practice of factoring. So if I looked at it in that fashion, and I think if you'll agree with me that 4u squared plus u minus 3 factors as 4u minus 3 times u plus 1. See, 4u times u is u squared, negative 3 times 1 is negative 3, and a 4u times 1 is 4u, and a negative 3 times u is negative 3u. 4u minus 3u is just u. Okay, so we've got, if we think that way, then we ought to be able to factor the above. Instead of a u, we have tangent of theta, don't we? So we have 4 tangent theta minus 3 times tangent theta plus 1. And notice 4 tangent of theta times tangent of theta, of course, is 4 tangent squared theta. Negative 3 times 1, of course, is the negative 3 at the end. And here we have a 4 tangent of theta times a 1, which is just 4 tangent of theta, and minus 3 times tangent theta, which is minus 3 tangent theta. 4 tangent theta minus 3 tangent theta is just tangent theta. So we've been successful in factoring that, and that's a technique that we need to be able to do. We need to be able to use that technique. Okay, lastly here, we have to factor cosecant squared theta minus cotangent theta minus 3. And we can't use the same technique that we used above. So we have to be a little bit creative here, maybe is the right word to use. Whoops. And whenever I see cotangents together and cosecants together, it reminds me of one of the other Pythagorean identities. This is the third Pythagorean identity, that 1 plus cotangent squared theta is equal to cosecant squared theta. And so my motivation here is if I could write it in a similar fashion to what I wrote up here, what we had up here, that I could get everything in one particular trig function instead of having a mixture of cosecant and cotangent. And cosecants can be replaced with cotangents in this fashion, cosecant squares, that is. See, cosecant squared theta is the same as 1 plus cotangent squared theta. And like we did above, we could replace cotangent squared theta with cosecant squared theta minus 1 by just subtracting a 1 on both sides. But what we need to do is replace cosecant squared theta. So that's the very first step I've taken here. I took the cosecant squared theta in this expression and replaced it with 1 plus cotangent squared theta. And then I noticed that I can rearrange what we have and add some terms. That is, I can take this 1 that I have here and subtract 3, that's a negative 2. So I have cotangent squared theta minus cotangent theta and minus a 3. And now, of course, it's not what we had above, but is of the form a u squared minus u minus 2, which we ought to be able to factor. Okay, and I've done that here. Cotangent theta times cotangent theta is how we get cotangent squared theta. A 1 times a negative 2 is how we get this negative 2. Cotangent of theta times negative 2 plus a 1 times cotangent theta, that's negative 2 cotangent theta plus 1 cotangent theta, which is negative cotangent theta in the middle. So we've succeeded in factoring after we were a little bit used some ingenuity here, actually, to be able to accomplish something. And these are the issues that we run into when we're dealing with expressions involving trigonometric functions. Well, again, we're going to do something on the next page, so let's move to that next page. Okay, you can see here now we've got two trigonometric fractions, if you will, and we're to perform the addition, add those two fractions together. So let's get started here. So all I've done is rewritten my problem here, and now I need to add these together. Now, to add them together, I need a common denominator, don't I? And the denominator I've got here on the left and the denominator I have on the right, the left fraction and the right fraction, they don't have any common factors. And so it's like if you have a denominator of 2 and 3, then the lowest common denominator is just 2 times 3. It's different if you have a denominator of 6 and 9. In the case of 6 and 9, to get the lowest common denominator, you don't multiply them together. That would be way too big, because 6 and 9 have a common factor. The common denominator there is actually 18. But when the two denominators have no factors in common, then the lowest common denominator is simply the product of the two. And so keeping that in mind, I've really made one big step here. What I've done is say, okay, I need to multiply this by the sine of theta so that I have 1 plus cosine theta times sine theta as my denominator. But if I multiply this by the sine of theta, then I've got to multiply the numerator by the sine of theta. And that's what you see right here. Okay. Now I look at this fraction and say, oh, I've got to multiply this denominator by 1 plus cosine theta so that I have 1 plus cosine theta times sine of theta. So I take this numerator and also multiply by 1 plus cosine theta, and that's what you see here. So I actually have two fractions, a fraction here plus a fraction here, and when I add those fractions together, I add their numerators, and that's what I've shown here. So I mean, I've taken a pretty big leap here, assuming that we're familiar with adding together fractions with different denominators. Okay. Well, what next then? Well, here's what's next. I can actually perform sine theta times sine theta, sine squared theta. And I can perform cosine theta times 1 plus cosine theta times cosine theta. That's actually cosine theta plus cosine squared theta. But notice And of course, the denominator I'm going to leave unchanged, because you normally don't multiply denominators out until you get past the stage of potentially simplifying. And we don't know what it is we're simplifying yet, so we leave it alone at this point. Okay, well, here's the next issue. You notice I wrote this in a different order, and that was because I noticed ahead of time that I actually have cosine theta plus cosine squared theta, but I rearranged it. And why did I rearrange it? Because I wanted you to recognize that sine squared theta plus cosine squared theta is in the middle of all of this. And that is just 1, isn't it? We know that from previous work. And so we can replace this part of the fraction with a 1. And so that's what I've shown here. Maybe. So, as I said, replace sine squared theta plus cosine squared theta with 1. So I have 1 plus cosine theta. And it's good that we didn't multiply out the denominator, because now we notice we have a 1 plus cosine theta factor in the numerator and also in the denominator, so that will reduce, won't it? That we can replace, we can reduce or cancel, we say. So we'll be left with a factor of 1 in the numerator. Remember, here's what's happened. Let's not forget what actually took place. We took this and canceled with this, didn't we? And so that leaves a 1 over sine of theta. And that's what I'm showing here. Now, I guess one other thing, 1 over sine of theta, maybe we would recognize the basic identity. 1 over sine of theta is the same thing as cosecant of theta. So we can take this sum and add together and simplify completely to cosecant of theta. Let's see what we have to do on the next page. Okay, here we're just asked to simplify. And one of the things that this expression, sine of theta plus cotangent theta times cosine of theta, and obviously there's no common factors here, and all the trig functions are different. And sometimes we're faced with things that look like this that we need to manipulate, simplify, whatever. And it's not unusual for me to always go back to the 2 basic building blocks, sine of theta and cosine of theta. So what I'm thinking when I look at this is that cotangent theta could be replaced with its ratio identity, cosine of theta divided by sine of theta. So that's what I'm thinking, that I can get everything in terms of those 2 functions, and that's what I've said here. Begin by rewriting the cotangent of theta in terms of sine and cosine, and that is that the cotangent of theta is cosine theta over sine theta. So I've taken the expression and replaced this with the fraction. Now, after I do that, there's actually some algebra that can be accomplished, and that algebra is multiplying this fraction with cosine theta. And of course, we could think of that as cosine theta over 1, and so we have cosine theta times cosine theta divided by sine theta. And so there's our cosine squared theta over sine theta. Now we have two terms that maybe we can add. See, now that we've got something we can work with that we didn't have before. And of course, to do that, we would need to write sine of theta as a fraction that has a denominator of sine of theta. And so that shouldn't be difficult. We just multiply by sine of theta over sine of theta. And so we have sine squared theta in the numerator, sine theta in the denominator. Now we ought to be able to add these 2 fractions together because they have the same denominator. Well, when we add the numerators together, of course, we have sine squared theta plus cosine squared theta, and divided by the common denominator of sine of theta. And then we recognize, and we've got to be good at this, then we recognize, oh, sine squared theta plus cosine squared theta is the same as 1. So we replace it with 1. And so now our fraction is 1 over sine theta, which we could write as cosecant theta. So once again, we've taken something that didn't look like we could simplify by making one change, it opened the door for lots of opportunities. So that's a good problem, a good thing to deal with, getting used to these ideas. Okay, on this next page, we're actually to the point of going through this process called verifying trigonometric identities, or establishing trigonometric identities, or proving trigonometric identities. And an identity, you know, an identity is different than an equation. An equation like 2x plus 1 equal 5. What would we do? We'd subtract 1 on both sides. We come up with a value of x, and we come up with a single value of x to solve that. Okay. Identities mean, it's called an identity, is that the equation is true for every theta that we can put into it. So what we're really looking at here is to say, oh, well, this would say that if we had the tangent of pi over 4 times the cosine of pi over 4, we know it's equal to the sine of pi over 4. Or if we had the tangent of 2 pi over 3 times the cosine of 2 pi over 3, we'd know it's equal to the sine of 2 pi over 3. That this is true for every proper choice of theta. There's for every theta that it makes sense for. We couldn't use a theta that would cause tangent of theta to be undefined. But outside of that, every theta. So that's what identities are about. So in this case, we're asked to verify this identity. And the step that you will normally take when you're asked to verify an identity is you start with the side that is most complicated. Okay. You start with the side because that offers you the most opportunities to manipulate. So I'm going to write down the tangent of theta times the cosine of theta. And we'll see that in a moment. And then we want to make algebraic adjustments to this left side that we started with, and that are valid until we change into the sine of theta, until it simplifies into the sine of theta. Now, as I said here, we can use a basic identity right off the bat and introduce the sine of theta. And here's what I mean. I started with the tangent of theta times cosine of theta. And I'm keeping in mind that I need to have a sine of theta eventually. So the first thing I thought of was replacing tangent of theta with sine of theta over cosine theta. So tangent of theta times cosine of theta is equal to this fraction times cosine theta. And I've introduced the sine theta along the way. Now, that algebraically can reduce because cosine theta will cancel with cosine theta, leaving sine theta, and we've established or verified this identity. Now, we've done one here that is extremely simple. It took one little change, and it simplified very quickly. Now, they're not always this easy, but this kind of gets us set up for what we might see in the future. Okay, for our second example of verifying trigonometric identities, you see what we're supposed to verify here. Secant squared theta minus 1 over secant squared theta is equal to sine squared theta. Actually, I'm going to do this in two different ways, but let's get started with the very first way. So here's the thing to look at. Because I consider this left side the more complicated, I'll start with it. And when I start with it, that means I write it down and put my equal sign, and now I'm going to manipulate this expression. Now, I'm not considering sine squared theta immediately. I know I'm trying to get to that, but I'm looking at this fraction saying, what can I do with this fraction? And I'm noticing a secant squared theta and a 1 in the same expression. So let's come over here and be reminded of a couple of boxes here that, you know, here in this top box are the 3 Pythagorean identities that we need to have memorized. There's not any question about it. Now, from those 3 particular identities, we can manipulate. So if we take this first identity and subtract sine squared theta on both sides, then we would have the first thing we have here. Or instead, if we subtract cosine squared theta, we would have this. If we look at the second identity and subtract 1 on both sides, we would have tangent squared theta is equal to secant squared theta minus 1. And likewise, with this one, if we subtract 1, this is what we would have. Now, I'm bringing this up because I recognize that I have a secant squared theta and a 1, and then I started thinking about it, and oh, well, secant squared theta minus 1 is the same as tangent squared theta. So we could replace this numerator with a tangent, actually, we could just replace it with tangent squared theta, couldn't we? That's what I said. But I guess what I did when I did this problem for the first time is I looked at secant squared theta up here and replaced it with tangent squared theta plus 1, and then subtract 1. So see, I could have done it in either way, and this is the way I chose to do it here. Okay, so after we use that, then we'll simplify the numerator to just tangent squared theta. And so this is the expression we have now. Now, a little bit of algebra, or recognizing, I guess there's several things we can do, but recognizing that secant squared theta, and that's just what we have to do, is experiment. And so that's, we got to get used to the experimentation. I might, now let's remember, we're trying to get this to be equal to sine squared theta. So it's about time to maybe introduce our trig functions, sines and cosines. And I know secant squared theta can be written as 1 over cosine squared theta. And for that matter, tangent squared theta could also be written in a way that we'll see in a moment. But using the idea of how we divide by a fraction, when we divide by a fraction, we multiply by its reciprocal. So this expression becomes our numerator times the reciprocal of our denominator. Now, of course, like I said, we could have introduced this earlier, but tangent squared theta I'm rewriting as, tangent of theta is sine of theta over cosine theta. And if we square that, we get sine squared theta over cosine squared theta. So we're in a position now that we actually have some kind of multiplication that we can simplify, because we see that the cosine squared thetas will cancel. And so we do get equal to sine squared theta, which is what we were trying to do originally. And that came about by introducing sines and cosines eventually. Okay. Well, on the next page, I want to give you an alternative way of doing this. And so let's just look there, and I've all of a sudden here, this is doing it a different way. Now, let's read. In fact, let me put a shade up to make sure that we concentrate on the pieces that I want us to concentrate on a little at a time. Now, here's another way to have thought of this. Rather than worry about this numerator, I've broken this into 2 fractions. See, when you have a numerator that is more than one term, you can break it into multiple fractions. But you can't take apart a denominator, but you can take apart a numerator because you can keep the denominator. Okay? And so we see that this subtraction of fractions is exactly what we have on this left side if we were to do that subtraction. Now here's the significance, of course. Secant squared theta over secant squared theta is just 1. And 1 over secant squared theta is the same as cosine squared theta, because the secant theta and cosine theta are reciprocals of each other. So we could have replaced this with cosine squared theta. And of course, then we recognize 1 minus cosine squared theta is one of those special alterations of our Pythagorean identity, and it can be simply be replaced with sine squared theta, which was what we were trying to show anyway. And just as a reminder where I got that, 1 minus cosine squared theta, I took this identity and I subtracted, in this case what I did is I subtracted cosine squared theta on both sides, and yeah, there were several steps here, weren't there? And so I can say, oh, well, in that case, 1 minus cosine squared theta is the same as sine squared theta. Okay. These are identities we saw on the previous page. I'm mumbling here, and I apologize for that. Okay, well, let's see what we have in store next. Okay, here to verify the identity, tangent squared theta plus 1 times cosine squared theta minus 1 equal negative tangent squared theta. And I don't know about you, but what's going through my mind right away is I see tangent squares and 1s and cosine squares and 1s, and so I'm thinking maybe some Pythagorean identities are in order here. So actually I'm thinking a couple of things. I need to start with the complicated side because I have more opportunities to change it, and once again it seems like the left side is the more complicated side. And so I'm going to actually refrain from multiplying these two things out first. I want to see that if I start with that left side, I could just start multiplying, but notice tangent squared theta times cosine squared theta, well, maybe that would work out nicely. I mean, it certainly might, but I think what I want to try here, and this is the case with identities, is that there's multiple approaches that can be correct. But what I want to try is I'm noticing tangent squared theta plus 1, and that's one of my important identities, so I can simply replace tangent squared theta plus 1 with a secant squared theta. Oh, but notice I've also replaced cosine squared theta minus 1. Now here's the issue. The cosine squared theta, cosine squared theta minus 1 is, oh, I don't have that. See, that if I look at this, if I take sine squared theta plus cosine squared theta, I subtract cosine squared theta on both sides, then I have sine squared theta is 1 minus cosine squared theta, just the opposite. But if I were to take that and multiply both sides by -1, as you see in this bottom, right down here, then I'd be multiplying the left side by -1, and when I multiply this left side by -1, I get -1 plus cosine squared theta, which is cosine squared theta minus 1. So cosine squared theta minus 1 can be replaced with negative sine squared theta, and that's what I've done. I replaced it with negative sine squared theta. Now, that may not have been the thing to do, but that's what I thought of, okay? So next we want to well, I recognize that secant squared theta can be written as 1 over cosine squared theta. So that's something I can do. Now, how useful it is, we're not quite sure. What are we trying to do? Oh, we're trying to get tangent squared theta, negative tangent squared theta. Notice below, I have a negative, that's going to help. And I have sines and cosines, it looks like that's going to help because I can think of tangents in terms of sines and cosines. And so multiplying these two together, I certainly get this fraction, a negative fraction, sine squared theta on top, cosine squared theta as the denominator. And then we recognize that, of course, and I'm going through some extra steps. That's the same thing as squaring the fraction sine theta over cosine theta. Sine squared theta over cosine squared theta is sine theta over cosine theta squared. And of course, sine theta cosine theta is tangent theta, so we have tangent theta squared, and of course the negative is in front of that. And so we have verified the identity. We've manipulated it until we see only the right side in its correct form. So perfectly done. This one's a little more involved. Verify the identity tangent of theta plus cotangent of theta is equal secant theta times cosecant theta. It's maybe a little more difficult to decide what we think is the more complicated side because we always start with a more complicated side. And I'll tell you what my thinking is here, that addition is more complicated than multiplication. So for that reason, I'm going to one more time start with the left side. Plus, when I convert tangent of theta and cotangent of theta into things I can actually add as fractions, then I'm going to introduce sines and cosines, and that's always a good thing when I'm trying to get secants and cosecants. So I'm taking the left side, and as it says, I'm going to convert both tangent and cotangent into their ratio identities, their definition in terms of sines and cosines. Now, I have two fractions I can actually begin thinking about adding. And to add them, I need a common denominator. And the common denominator is just simply going to be the product of these two denominators. So for this fraction, I need to multiply by sine theta over sine theta. For this fraction, I need to multiply by cosine theta over cosine theta. So that results in sine squared theta numerator here over the common denominator cosine theta sine theta, and likewise cosine squared theta over the common denominator here. Now, since I have a common denominator, I'm in a position that I can add these fractions, and to do that, I simply add the numerators and of course divide by the common denominator. And you may have even noticed ahead of time what was going to happen, because that numerator, sine squared theta plus cosine squared theta, we ought to think of 1 immediately. Okay, we ought to think of 1 immediately. So now we have something much simpler. Now, let's go back up here and remind ourselves what we're trying to get. Secant theta times cosecant theta. But remembering, secant theta is 1 over cosine theta, and cosecant theta is 1 over sine theta. Look here. I have a cosine theta in the denominator and a sine theta in the denominator. So I could think of this fraction as 1 over cosine theta times 1 over sine theta. And that's actually introducing the pieces I need, isn't it? Because 1 over cosine theta is secant theta, 1 over sine theta is cosecant theta, and that's exactly what we were trying to get on the right side, isn't it? So another one completed successfully. Now these, I'm making these look simple because I have a lot of experience. What I'm really trying to do is give you some techniques and some explanations. You're going to have to struggle with identities on your own. I mean, they're not always simple. And sometimes you go down an alley and you find out that it's a dead end and you have to start over. So be prepared for that. And remember, in all of these videos, you can pause and try to work ahead. You can back up, reverse it. You can not even look at them, but I think that's a mistake. Well, I want to finish with a summary of how we deal with verifying identities. Remember, we first started with, though, algebraic manipulation, if you will, of trigonometric expressions, because we use those to solve equations, we use those to deal with identities, we use those techniques for lots of things in trigonometry. But on the next page, I want to summarize dealing with verifying trigonometric identities. And as you see here, I've called it guidelines. Well, the very first thing to recognize is that you work with one side of the identity at a time, and you usually work with a more complicated side, and you keep changing little pieces at a time. Once you've changed a little bit, then you change on the next line a little bit more until you morph it into the other side, either the more simplified side as we consider it, or the simpler of the two sides. But you start with one side. And then what I've stated here is we look for opportunities, as I'm reading it, to use the basic identities. We look for opportunities to use the Pythagorean identities or the basic identities like tangent of theta is sine theta over cosine theta, and so on. And note which functions are in the final expression that you want. So, sines, as it says here, sines and cosines pair up well, as do secants and tangents, and cosecants and cotangents. We kind of keep an eye on what we're trying to accomplish eventually, but we don't let it run our manipulations. The third thing to do is look for opportunities to factor an expression or add fractions or square a binomial, which we didn't do, or create a monomial denominator, which we didn't do that either. But as you experiment, as we see other things later on, maybe those will become more apparent. if 1 through 3 do not help, try converting all terms to sines and cosines. And a lot of times I just go back to the basic building blocks, I call them. Now, to end with, always try something. It's like writer's block. If you're not careful, you can sit there and stare at it and say, I need to know from the beginning to the end what I'm going to do. It doesn't work that way. You start, you try something. Then if you don't feel like you're getting anywhere, you start again and try something different. That's what you end up doing. They're not easy always, but we need to work and be good at recognizing patterns, recognizing places that we can use existing identities. That's very important in your study of trigonometry and later on for calculus. Well, that's all I have about trigonometric identities. I hope this is useful, and good luck on your homework.